Okay, hello everyone. I'm Robin Hartley and I'm here to present my research into the effects of particle reinforced interleaf architecture on composite toughness. So, as we all know, composites are limited by their susceptibility to impact damage, taking the form of cracks that coalesce in interlaminar regions and act as initiation points for catastrophic delamination. An established way of preventing this is to incorporate a tougher region of increased thickness between fiber layers called an interleaf. Interleaf technologies that have been qualified for use on aircraft often use particles to form these regions, as they allow the interleaf thickness to be controlled relatively easily. The motivation behind this research is to determine the effects that changing different interleaf characteristics have on the interlaminar toughness. So the aims are to look at the roles that interleaf thickness, particle material, particle loading, and loading mode had on the toughness, toughening mechanisms, and crack path in interleaf composites. And the approach I took was to start with the base constituents, formulating a high-performance epoxy matrix and sourcing two particles of similar dimensions, one hard and made of glass, and one soft made of polyamide 12. Next, I investigated the toughening mechanisms present in the neat resin and how these differed between the two particles. And finally, I manufactured prepreg and particle-filled resin films for testing in mode 1 and mixed mode. So here we see a plot of interleaf thickness against mode 1 critical energy release rate, where the orange line is for interleaves containing glass particles, the blue line is for interleaves containing polyamide 12 particles, and also plotted is the baseline value in green, for the baseline interleaf value. So also plotted at the critical energy release rates from testing the equivalent neat resins. So looking at these neat resin, and these are the dotted lines, looking at those neat resin results, you can see that glass particles are not very effective tougheners, as they can only toughen through crack deflection mechanisms and by acting as stress concentrators that enhance toughening mechanisms such as shear banding that are already present in the particle-free resin. The polyamide particles, on the other hand, have a significant toughening effect, which can be attributed to a combination of their ductility and interfacial strength with the epoxy, which basically allows them to tear and plastically deform as the crack propagates past them. The other thing to note is that although the mode 1 G1C values increase with interleaf thickness, they never actually match the values achieved in the resin tests, and this is true at all interleaf thicknesses tested in this study. This is because the full development of crack tip plastic zone is constrained by the adjacent fiber layers. The glass particle interleaves are much closer to reaching the equivalent resin value, indicating that at 67 microns here, that's close to a fully developed plastic zone for this material. However, there's a much bigger difference between the polyamide particle interleaf values and the equivalent resin at comparable thicknesses. This indicates that the ductile particles promote the formation of a larger plastic zone. Now, the important thing to consider here is that when cracks propagate through interlaminar regions, they're not utilizing the full fracture toughness of the resin. Now, this is especially true when you consider that a commercial interleaf system will have interleaf thicknesses between 20 and 30 microns. So you're not going to be getting up to these very thick interleaves where you get enhanced fracture toughnesses. Another takeaway is that particle material is crucial. These particles are not just acting as spacers to increase the thickness of the interleaf, and their properties are very important. And it would appear that beneficial properties would be a low yield stress and a high interfacial strength. So that is the end of my presentation, and I'd like to thank my supervisors and Hexcel for the support they've given me during this project.